Next up, the final thing we need to cover before we get back into programming the to-do list application is we need to touch on recursion. And the reason we're going to touch on recursion is that this is what we use for looping in the functional programming world. So if you're not comfortable or familiar with recursion, you'll really want to understand this before we go on. As I noted in the book here, I spent over 50 pages explaining recursion in my book, Functional Programming Simplified. But since then, another thing I did was I wrote a booklet on this topic, and this is a free booklet. It's a free PDF, and you'll see the URL here. So if you're interested in that free PDF, this is over 100 pages of content about recursion. So I'll cover it briefly here, and then if you want more details, see this free booklet. So as I show here, a recursive function is just a function that calls itself. And to demonstrate this, I want to create some examples. So my first example here is a recursive function, and what it does, it counts down to 0. So I named it countdown, and if you give it a value like 3 here, you'll see that it counts down to 0 like that. So let's go ahead and work on creating that function. And the first thing to note here is I'm going to go back to that approach we used with word count, and I want to look at this code right here and say, well, the first thing I know is that countdown is a function, of course, so that's why I'm coming over here and I'm creating a function named countdown. That's the first thing that's obvious from this code right here. And then the second thing that's obvious is that this takes one integer parameter as the input value. So then I come over here and say, well, as I'm sketching this, of course, then I want to take one integer value right here. Coming back over here, you can see there are no results. There's no return value here. I don't have val equals countdown of 3. I just have countdown of 3. So this is being used as a statement, and this is being printed out. So that tells me in our type signature that this is going to be unit right there. It's going to have a unit return value because it doesn't return anything useful. It just prints some output inside of here. And again, this process of sketching this function signature is exactly what I showed in the word count area. And I really love doing this in functional programming because, as I mentioned, pure functions, even though this one isn't pure, you can still sketch function signatures like this just by looking at the example of what someone wants, and then you can come over here and start sketching that signature. As I note down here, normally I implement most recursive functions as match expressions, but to keep this one simple, if you've never used recursion before, is I'll use an if-then expression inside the body here. So this is one thing to know, and then a second thing to know is usually when I write a recursive function, I specify that end or stop condition first. And that's because I always want to make sure the recursive function is going to stop. And that's because the function is calling itself as fast as possible, and what I want to make sure I do is tell it where to stop right away. So I think about that condition, and in this particular case, I know that I want the recursion to stop when the integer parameter here is 0, so I can go ahead and write that condition first. So as you see in the book, there I have if I equals 0, then what I know I want to do is I want to stop the recursion right there. I may not know exactly how to stop the recursion, but I know that I want it to stop. And now I want to come back to the book here and show this. So what's going on here, or what I'm about to do, is I'm about to put this symbol right here. So this symbol, the open and closed parenthesis right next to each other, this is the one and only instance of the unit type. So this is actually a value. So what's going on is when this function stops here, I need to make sure that I have the unit return type. That's what I need to have is the return type. So in this condition right here, what I do is I put that value there. And again, this is the one and only unit value in the Scala world. So now I've guaranteed that when I equals 0, I'm returning the unit value right there. So that's the stop condition. So now that I have that stop condition, I want to start thinking about the rest of the algorithm. And that is, what do I want to do here in this else position? What is the algorithm right here? I think, well, what is the algorithm right here? Or what is the purpose of this function? And of course, the purpose of this function is to print that output that we saw earlier. So this is just going to say print line I. So that's going to print whatever I is at this point, is going to print it. And then the next thing I do is I recurse. So I go down and I call myself again. And this is the second key here, is that when I call this function again, I need to make sure I, in this case, decrement that value. So I want to do I minus 1. So now you can imagine that when countdown is called the first time, I here is going to be 3. So then it says Is 3 equal to 0? No, it's not. So then we come to the else condition. We print the 3, and then we call countdown right here with 3 minus 1, so that's 2. So now we come back up here again, and now countdown is called with 2. Is 2 equal to 0? No, it's not. We come down to the else condition. We call print line of 2. Then we recurse again, and we call countdown with 2 minus 1, which is 1, of course. So now 1 is the input value. Is 1 equal to 0? No. Then come to the else condition, print line 1, and now 1 minus 1 is 0. Okay, so then countdown here is called with 0. Is 0 equal to 0? Yes, it is. Okay, in that case, we're going to stop right here, and we're going to return unit. And then we come out of this function call, and we come out of every function call that was made before that. So if I add a countdown here, and you can imagine, I'm going to shorten countdown to just the letter C. So you can imagine the countdown was called with 3, then countdown was called with 2, then it was called with 1, and finally it was called with 0. And what I was saying was, once it's called with 0, then we come to this part of the code right here, and now instead of recursing downward as we were doing here, down into more countdown functions, what happens is this is the end of the countdown function. It comes out here, it comes to this unit type, and now the flow starts going back this way. So when we were descending, maybe another way to say that is when we were descending in the calls, we were going in this direction, call countdown again, call countdown again, call countdown again. And now what we do that we've reached this condition is we unroll, and everything comes back out of here like that. And now just to prove that this works, I can create a main function here, and I will just call it main. And here we can just call countdown of 3 like that. And then I save that, and I have this compiling and running over here, and there you see the output 3, 2, 1 right there like that. So this covers the basics of recursion. And if you want to see one more thing, what I could do is say, put a little debug information here, and then say, well, I equaled 0. How about that? So just to be very clear, I'll just say debug like that, save that, come back over here. And there you can see, so it printed 3, 2, 1 just as we wanted to. And then when it comes over to this block here, it prints that debug statement, and then the recursion ends. As I mentioned, I really like using match expressions when I write recursive algorithms. So what I want to do is get rid of all that code. I guess I keep that code right there for just a few moments. And put it down there, mostly just so you don't have to watch me type. And now what I do with match expressions, the way you start them is you say I match. So I is the variable name, and now we want to start a match expression. And I always start with the end case first. So as I noted before, the end case is when I is 0. So we say case 0. And then just like before, we transform that into the unit type. So that's all you have to do right there. This is the end case. And then here, this other case is everything else. So everything else, when you're writing a match expression, you just handle it with that underscore character like that. And now we do that, and then I can bring this code back up here. And if you like to see things aligned like that, then that is the match expression. So again, we have the two cases. The case 0 is the end condition. When I is 0, that's when we end and return unit. And for every other situation, we do this code down here. So let me move that up there, save that, and come back down here. And we see that result right there as desired. So that's a first look at a match expression. And now a lot of times when you're writing match expressions, you're working with the Scala list. So I'm going to have a list like this one, 1, 2, 3. And as you can see, that creates a list event. But a different thing you can do with a Scala list is create a list like this. And this goes back to the Lisp programming language, Lisp. And now this code right here is exactly equivalent to this code right here. You can see they both create the list of 1, 2, 3. But knowing this part is very important for what we're about to do. And that is that a list consists of all these elements right here. So the first element, the second element, the third element, they're all separated by these colon characters. And then when you get to the end of the list, you have this element. I refer to this one as the caboose element. And it's this special nil value. So a nil value is always at the end of a list. And in fact, if you try to create a list without a nil value, you'll get something different, like this error. So again, nil is always the last element in the list. And this is very, very important for when we're writing recursive functions. And basically, when you're writing recursive functions, you're deconstructing a list. And your two conditions in the list are always going to be, well, what is the nil case? And then what is the case for every other element? And that's actually very similar to this code up here. And you'll see in just a few moments as I do this, we'll be saying, well, what is the nil case here? And then I'll do something like that. And then the other case is over here. And you say, well, for everything else, what do I want to do right here? And this part, actually, to make this more correct, is going to be do your algorithm here and then call yourself recursively here. That's actually more accurate than what I just stated. So again, nil case is the end and everything else goes here. So now my favorite way to teach recursion is by using a sum algorithm. And the way you can think of this is a sum algorithm is going to take in some list. And in the book, I call it list. So to be consistent, I'll do that. And we're going to say we want to take in a list, and just to keep things simple, we'll do a list of int. So sum is going to take in a list of integers. And we also know that sum is going to create the sum of that list of integers. So that is also going to be an int. So that gives us the return value. And just as I have done before, we just sketched the function signature right here. So again, I love this part because I got this part out of the way, and now I know exactly what's coming in and what's going out. And as I mentioned, when you're working with a list, the first thing you do, the end condition, is always that nil value. So you're going to say, well, what do I want to do when I get to this nil value here? And this one is very interesting. So here we get into this thing called the identity value. So there's something called an identity value or an identity element. And in short, when you're working with a set of integers like we are, and you're also working with a sum algorithm, the identity value is 0. And what this means is that when you're summing a list of integers, the value 0 adds nothing to the sum. So I always think it like this way. You have a set of data like this, and then you have an algorithm that you're trying to work with. So what is the identity element? Where that identity element is something that won't change the value of this algorithm right here. So when you're doing a sum on a list of integers, the value 0 adds nothing. And similarly, I note that if you were doing a product algorithm where you're multiplying all these, the identity value there would be 1, because again, when you're multiplying things, 1 does not modify that value. This is real key concept, as I note here, when you're working with recursion. So now when we go back here, we could say, well, we're working with the sum algorithm on integers, and our identity value is 0. So I can return 0 here, and that won't affect the sum. And now the way you write the other condition looks like this. So now we could say something in the book. I use head and tail, and notice that I used those two colon characters before, just the way I had constructed a list. And now we say, well, when we have these head and tail elements, we're going to go ahead and say, well, what I want to return here, this is where the sum algorithm comes in. I want to return the sum. And just to back up for a moment, the head element is the first element in the list. So I want to return the sum of the head element plus the sum of all remaining elements, the tail elements. So if I come back over here, and I'm just going to line things up a little bit just to make this easier to read. So again, I'm returning here the sum of the head element plus the sum of all remaining elements. And these don't have to be called head and tail. And in fact, in other situations, I'll refer to this as x, and then refer to this as x of s. And now that could even give you a better idea that this is one element here, because we call this one x, and then we call this one x's or x of s. This, in the functional programming world, typically when you see x of s or y of s, you're talking about some sort of list right here, and then this is one element. So again, the algorithm is the first element plus the sum of all remaining elements right here. But a nice thing about head and tail, I'm just going to use h and t now, is that it's a little more meaningful right there. Actually, I went back to this code of using head and tail right here because this is a very important concept. So what this means is if you have a list of, let's say, 1, 2, 3, like that, then in this particular situation, the head is going to be that first element, so that's going to be 1. And then the tail is going to be a list of 2 and 3 right there. So this is extremely important to know. So now this is 1 right here in this position, and now this list is 2 and 3 right inside of here. And I wanted to make that clear. And I think that's more clear now actually when I use head and tail compared to x and x of s, is that this guy is being passed into here. So when this is called the next time recursively, now we have the list of 2 and 3, and then that comes down to here, and then in that second call, now this one is going to be 2, then we'll have a list of 3. So then you can imagine a list of 3 being passed in here, and then control comes back up here, this gets a list of 3, we come back down here one more time, so now the head is going to be 3 in this case, and then now that we've reached the end, what happens is the tail becomes nil. So now sum is called again. This time it's called with that nil value. So of course it comes to this case right here, and that's when 0 is returned from the sum function. So if I get rid of all those comments and get rid of that, now we could say, well, what I want to do is just, how about if I print line the sum, or if you prefer, what I could do is say val x of s, just to do one step at a time. X of s is 1, 2, and 3. And then val the sum equal, actually let me not call that something else, val a equals the sum of x of s, and then we can do print line on that a. So I clear that out. Now I want to get back to compiling and running this. And I'm missing a very important thing here is the start of the match expression. So list match. And now I see that result right there, 6. And a nice thing about this is you can also put some debug information here. So if you want, you can say print line and just say, oh, this is the head and tail section right there. And then here I could say, this is the nil situation right there. So go ahead and save that again. And now you can see the 3 head and tail calls right here. So head and tail, and then that's followed up by the nil debug statement, and then that's followed by this result 6 right there. So I hope this is a decent introduction to recursion. And as a note in the book, once you get into recursion, you're also going to want to learn about this thing called tail recursion. And that's especially true if you're working on the JVM. And there you get into these concepts of stacks and frames. And I'm not going to get into all that here, but if you want to, you can find that in my functional programming book. Or again, you can find that in my other free booklet, which is called Learning Recursion. So this is the last just-in-time lesson. This one was on recursion. And now the next thing we're going to do is get back into programming the to-do list application.